Hello chemistry students. In this video I'm going to go over vapor pressure and more importantly Dalton's law of partial pressures. So just so you understand what's going on with this, vapor pressure is the pressure that's exerted by the vapor in equilibrium with its solid or liquid phase. Now you're like, what's that? Well, you know how water evaporates, right? Well, lots of liquids evaporate. Gasoline, the stuff that's inside of that aerosol can that you use to spray stuff with. And the reason why they tell you not to dispose of those cans in fire is because the vapor pressure increases as the temperature increases. In other words, the can will explode if you dispose of it in fire. You may have noticed that just if you let a drink sit out and get hot, and you might have noticed that the bottle kind of swells a little bit or something. So the reason for this is that the liquid molecules move faster at higher temperatures, escape into the gas phase more easily. So basically what you can imagine here with vapor pressure is anytime there's a liquid involved, that liquid is going to be evaporating. And the higher the temperature, the more it evaporates, and the more vapor pressure you have. Okay, so just some examples of that here. So you see water evaporating off of a lake, and this is the summary of what's going on there. And then if you increase the temperature, then the water evaporates more readily. And you can imagine that the pressure would increase greatly if you capped off that teapot. Now, in the atmosphere, you can see an example of, well, you might not be surprised to learn that there is a little bit of water vapor in the atmosphere. It varies depending on location. It's really high in tropical rainforest kind of areas and really low in desert areas. But the atmosphere is a mixture of gases. And Dalton's observation was that if you took two gases, we're getting into Dalton's law of partial pressures now. Dalton's observation was that if you took two gases and combined them into the same size container, that those two gases would have a greater pressure than either gas individual. In fact, Dalton noticed that when you added the two pressures of those two separate gases together, providing they don't react, like nitrogen and oxygen, you can combine those without them reacting for the most part. And he noticed that, you know, if you had 186 millimeters of mercury of nitrogen and 93 millimeters of mercury of oxygen, combine those together, and got the sum of that, which is 279. So that's a pretty simple relationship. You take two things, add them together, and you get a sum. So this is Dalton's law of partial pressures. If you take two gases and put them in the same container with each other, then the pressure of each of the individual gases add up to the total pressure. Okay, that can be stated in this way. The P total equals PA plus PB plus PC plus PD. You can just keep going. That equation is on page 3 of your reference table, should you ever want to look back at it. It's stated as PT equals P1 plus P2 plus P3. So instead of A's and B's and C's, it uses 1's, 2's, and 3's. Alright, so for example, this one shows, you know, hey, if you got 32 or 0.32 atmospheres of water and 0.16 atmospheres of oxygen, together the total pressure would be 0.48 atmospheres. Alright, so total pressure is the sum of partial pressures. That's Dalton's law. Now, this works when the gases are evenly mixed and in the same container. Alright, you might notice, or if you've ever learned anything about scuba diving, you might know that when you do really deep dives, the nitrogen can actually dissolve in your bloodstream, and then when you come up you start to get bubbles of nitrogen in your blood, which is a condition known as the bends. So when you do really deep dives, they use helium instead, which is not as able to dissolve in your blood, which also probably gets really expensive. But anyways, Now, here's an example of where you might see something like this used in chemistry. So you do an experiment that produces a gas, collect a tube, or use a tube to collect the gas by bubbling it underwater. So you fill this bottle up so it's completely full of water, and then this gas bubbles in, the water goes out into the container, the gas gets trapped in here. Well, here's the deal. The water evaporates too. So not only do you have water, or excuse me, not only do you have the oxygen gas that you bubbled through, but you also have a little bit of water vapor in there. And so Dalton's law is necessary to subtract the vapor pressure of the water from the total pressure of the atmosphere to get the oxygen pressure. So here's this chart, and there are lots of these out there. This one happens to be in millimeters of mercury. You can find them in atmospheres as well. Based on the temperature, you can look up the vapor pressure of the water. So for example, you could have a student that collects some hydrogen gas over water at 20 degrees Celsius and 768 torr. What's the pressure of the hydrogen gas? Well, there's going to be hydrogen gas and water vapor to make a total pressure of 768. So at 20 degrees Celsius, the vapor pressure of the water is 17.5. Subtract that from 768 to get 750.5 torr. That would be the pressure of just the hydrogen gas at that particular temperature and pressure. All right, so I'm going to go out and show you an example problem. All right, so this is a pretty involved example problem, so we'll work through it. We're going to use Dalton's law of partial pressures as well as the ideal gas law to completely solve this problem. So, our unknown, eventually we want to get the moles of oxygen collected. Knowns, they tell us a lot of stuff here. So they tell us that we're at 25 degrees Celsius or 298 Kelvin. We're going to go ahead and convert that. Okay. All right, the volume of the gas is 95 milliliters or 0.095 liters. They also tell us that the total atmospheric pressure is 0.93 atmospheres. All right, now the thing that we have to realize as we work through this is that this oxygen gas was collected over water. So we're going to have to subtract out the pressure of the gas, or excuse me, the pressure of the water vapor from the total pressure to get the pressure of the oxygen. So it's going to be P total equals P oxygen plus P water. All right, and something that's really inconvenient for us is that this is in a different unit than the table that we had over here. So let's look back for a second. At 25 degrees Celsius, the vapor pressure of water is 23.8 millimeters of mercury. So I'm going to convert, you don't have to do it this way, but I'm going to convert the atmospheres to millimeters of mercury. You could do it the other way. Anyways, all right, so I got my total pressure is 706.8 millimeters of mercury. Okay, so 706.8 millimeters of mercury. I really jumped into the solve here, didn't I? Let's see. So the pressure of the oxygen we don't know yet, and the water vapor pressure we looked up, and it was 23.8 millimeters of mercury. All right, so we'll subtract to get the pressure of the oxygen. All right, when I carried that out, I got that the pressure of the oxygen is 683 millimeters of mercury. Now, that's not what we want. So we want how many moles. So once we get to this stage, I've got pressure, volume, temperature, so hopefully that will bring back to you also to remember, hey, look, I know something that has pressure, volume, moles, and temperature in it. I just have to look up a gas constant for that thing. So solve for moles, I'm going to do PV divided by RT to get N by itself, and plug in this is why we did all this work. Okay, this as our pressure. That's the most important part. Okay, you gotta know to subtract out that vapor pressure of the water. So 683 millimeters of mercury times the volume, which was 0.095. Divided by the gas constant, 62.4 liters times millimeters of mercury over mole Kelvin. Right, and put in our Kelvin temperature, which was 298. And cancel out some units here. Some millimeters of mercury cancel out, liters cancel out, kelvins cancel out. And that leaves you with moles. All right, so we'll carry out that calculation. All right, and once I carried it out, I got 0.003489, which will round to 0.0035 moles of oxygen. That is a small amount of moles, but this is a pretty small amount of gas too. Thanks for watching.